Um, so today I'm going to talk about a project that we did about a year back. Um, this was actually I learned Spark from Holden's book. So um, getting the introductions out of the way, I work at Elsevier Labs. Um, my email address is here, up there, in case you have questions and you want to email me. I write a blog, and I've lately started working with Twitter, and so work, as a user. Elsevier probably doesn't need an introduction in Amsterdam, but in case you don't know who it is, they are the world's largest publisher of science, technology, and medicine books and journals. And we have a lot of data, and both in terms of content and metadata, and we use them to, inform and enable customers, right? Our agenda today, so I'll describe the problem, then I'll describe our solution, briefly touch upon the other uses that we came upon that, and describe a little bit of future work, and then we'll do Q&A, right? Okay. So our problem was basically to migrate the Science Direct search engine from, so it was using Microsoft Fast initially as the search engine library, and we wanted to move it to Apache Solr. For those of you who are unfamiliar with Science Direct, it's a search engine for scientific documents, usually journal articles, book chapters, and so forth. It has approximately 14 million entries in the index, and that comes from about 3.5K journals and about 35K books. So it's fairly big, right? So this was our business problem. And then, so we really, when we wanted to do the migration, our main goal was that the customer should not even feel any impact, right? It should be like seamless. So the metric we came up was that the full text downloads from Solr should equal or exceed that from Fast, right? And the full text downloads are the little PDFs up there. What happens is that since we are a subscription-based model, so if your university or institution has a subscription to that particular journal, then it's free, it's bundled with a thing. Otherwise, it's like a pay-per-view model, so you click, you pay, right? I mean, if you want to see the content. So that was our metric. And so we went about it typically like most people would do. We set up an A/B testing framework. We piped the content 50 here, 50 here. And we saw how it behaved, right? We looked at the analytics on both sides and kind of matched them up, right? There were problems with the A/B test, though. First off, to do an A/B test, you have to deploy the search engine to production. And deploying is expensive. And we were doing A/B test, the frequent testing approach. If you have attended the A/B testing talk, we actually use p-values, which means that you need to run it for a particular length of time before you can get decent results. And the other thing is that it's risky, right? So you don't want to risk showing a really bad result to a customer and having him go away. So for these reasons, the scope of improvement was very limited. People were afraid to push changes, right? We could not push two changes at the same time because we didn't know how they impacted each other. And so it really kind of stalled. So what we really needed was something that, almost like a unit test for the relevance engineer, right? Something that could be run offline, something that could be run without deploying to production, and which produces something repeated, like an indicator. So that's the tool we built, and this is what I'm going to talk about today. All right. So, actually, I can see it here. So we have the inputs to our system was basically the query logs and the click logs, right? So if you look here, so this is like the cartoon, right? So the user basically enters a search query, right? And that query gets captured in our query logs. And then in response to that query, the engine responds with a page of results, like 25 results. And then among those results, the user may or may not, 0 or more clicks, right, on the full text results. Those get transferred over to our click logs. And so this is what we have. And then from what we can do is, given a reference set of query logs, we can replay these query logs against a new search configuration, right? So that is the approach we followed. What we had was, from our latest A/B run, we started, I think, about after the third A/B test, we started building this. So our reference set was from the third A/B test from the FAST system. About 800,000 queries, and the clicks that the customers had placed in that. So using these 800,000 queries, we could, and we would run against our new, experimental systems and get back the results. And combining, and so the net result of these three things, right, the query logs, the click logs, and the search results, allowed us to compute something we call the click rank distribution. So here's, this is the definition of our click rank distribution. I'll leave it up here while I just, tell you kind of what it means. So assume that in your reference set, you had a query, say, call it like PyData, right? Or so now assume that there was the reference set had the second entry, the second result, which was clicked, right? So now in your new data, in your new index, you run the same query, you replay the same query, and in this case, your new search engine brings that same result up in the first position. So intuitively, your new search engine performs better than the old search engine, right? Whereas if it was something that placed it in the third position, it performs worse, right? So this is only for one query, but now imagine that you run it through all the 800,000 and you compute an average. And that would give you kind of an intuitive metric by which to grade your search engine against your reference set. So mechanics-wise, what you do is for each query, you get all your click logs, and that's your document set CQ. Then you take, for the same query, you take the results that you got from your replayed logs, you calculate the intersection, you get the ranks, and you get your average rank. That's it, right? So this is what we did. And fortunately for us, the query and the click logs were already merged by the A/B test framework. They gave us a line-oriented JSON format like this, in which you had mainly two things that were important for us: the query and the document ID. So this told us that for this query, this document was a clicked result. The click rank was important only when setting up the initial reference set, not later on, because we don't need it after that. We already have that. So in order to generate the search results, we actually use Python multiprocessing rather than using Spark. Actually, using Spark to hit HTTP-based servers, where you have timeouts, is actually a bad practice. It turned out to be a good thing. I was able to actually use a T2 medium server, which could spawn 20 clients against a Solr machine and run without any problems, whereas I had numerous problems with Spark, with timeouts. So I'm going to show you some code. Mainly, just to show you how easy it is to actually do the multiprocessing. Essentially, it's the last two lines here. The num clients is the number of processes that I spawned, essentially Solr clients, in order to grab the search results. And then against the pool object, this is the multiprocessing pool object, right? And I run a map with two things. This one is a function that tells it what to do with a single instance of a query, right? And this one is a list of queries that it has to work on, essentially a list of functions, list of function parameters, sorry. And if you look up, you'll find that the download search results is essentially taking a query and a query ID, sending the result to Solr, getting back with the results, and writing it out to a local disk, right? The query list, on the other hand, essentially looks at your old, this one, right? And parses it out using JSON and gets the query. We also grab the query IDs, right? And This is the only time I'm able to get the query and the ID together in a sequential format. So this is where I actually pull out a kind of a mapping of the IDs and the query, right? I'll use it later. So this is what I did for the search results. So the output of this process looks something like this. For each query, I get a single file, right? And within that, I have this is from Pandas, so it's nice and clean. But it's essentially tab separated, right? So if you look up here, the file name is important for me because I have the query ID in there. The last bit where it says rewind -1, 1 is my query ID. And then I have the EID, which contains my doc ID. Reason I have this is kind of because of legacy. I had to follow what the original reference set was in because I could reuse my code that way. But I can grab whatever I want from here. So only two things important here. Once I got that, it's actually fairly easy to use PySpark to compute, and so getting the click logs and the search results, and using PySpark to compute the click rank distribution. So once again, I'm going to show you code. So this is like a skeleton of a PySpark program, really simple. I was using AWS with a 3-node EC2 cluster and all my data on S3. Right? So if you look, there's really 3 blocks, right? There's the imports, then there is the part where you create a Spark context. The Spark context is kind of central to everything. You will need the Spark context to get everything out of it. And because I was reading and writing to S3, I needed to set my the secret key and the access key. This apparently is no longer, it's kind of deprecated. There is another way to do it. I'm not sure how, but there is another way to do it. It's not encouraged, but it still works. So, and finally, you put your code in here, and then you stop the context when you're done, right? Okay. So now let's go to the code. So I have 3 steps. Step 1, I take the clicks data and convert it to this common, kind of a canonical format, right? The query ID and the list of click PIIs. So again, let's go from the bottom up. So here's my clicks text, the original line-oriented JSON that you saw. I run it through a map. So essentially, I'm reading each line of that file, and I'm parsing it out. I'm parsing out the query and the click PIIs from there, right? And then, so the next line, so what I get out of here is really the query and a list with a single click PII. The reason I have a list will become apparent really soon. So the next one is basically like a flatten operation, a group by key, except that I'm using the more performant reduce by key. And I'm passing in the addition, the reduce operator here, right? The reduce operator is a canned one from operator.concat. Essentially, instead of it's adding, it's basically concatenating lists, which is why I have a list here, right? So the output of this is basically my query and a list of click PIIs for that query, right? But I'm still not done, right? Because I need to have my key as my query ID. So here's another thing I did. Remember the ID file that I created when I created my search results, right? So that already has a number and the query. So what I did from here was I created a map. I extracted this. I collected it as a map. And then I broadcast it to all my workers. This is another strategy which saves you on a join. So essentially, this is like a join. We call it a map side join. But it's really just a filter, right? If you think of it, I mean, you get it. You essentially look up on the workers. You look up this map, right? The big QID map.value, and this gives you back the QID. So this gives you what the first step of your job. All right. The second step is basically to do a very, very similar operation on the search results. So recall that our search results were, 1 file per query, right? So I have this 800,000 files in my directory. So the way to read it is using the whole text files method, which treats each file as a single record. And then once I get it in, it gives you back like a key-value pair with the key as the file name and the value as the contents of the file. So which I send to parse file, and that essentially all it does is it strips out the two columns and then flattens out all the document IDs for the search results, right? So now the end result here is that I have a query ID and a list of result PIIs, right? PIIs are internal document IDs. Think of it as document ID. The last step basically computes the click rank. Now that if you know recall the definition of click rank, it's basically the intersection, right, and the average rank of the intersection, right? So when you do a join, you join on the QID, and essentially now you get a pair with the click PIIs and the result PIIs, which you can pass to the click rank function, and which does essentially that. It just computes the intersection, computes the dict of the IDs, and it calculates the click rank and it gives it back to you, right? Okay. So once you do that, so the output of this step is basically a list. So I also, so once I do the join, I coalesce it into one big file because this is a distributed operation, so it would have a number of different files. So what this one does is it takes all these different files and puts it into one, so it's easy to download. It's just simple one file download. And I save it to a text, and then, so once this is done, I download it and I use matplotlib and regular formatting operations to create reports. I'm not going to show you these because everyone knows about matplotlib and it's not very interesting. So one of the things that we did, so this is a result of multiple runs that you saw here for different engines. So it's got actually, this is my reference set, 1, 2, 3, 4, right? So, and 4 runs. And you put these, the click rank distribution side by side in the form of box plots. And the red line is the median, the dots are the averages. So it gives you like at a glance, you can see all the, the 4 different, the search engines. There are some other reports also, but this one was kind of, like the top level report that we used to show. All right. So ultimately, this was our internal stuff, right? So the next A/B test, we were actually able to reach 99.6% PDF downloads, and in terms of PDF downloads. Like I mentioned, we were doing p-values, so the difference in download rates were not statistically significant, therefore we passed. So, we kind of succeeded putting Solr in production. So I'm just going to cover some other uses. So since we got all this data, we had, we put it to various other uses, and I thought this would be interesting to show here. So one of them was to measure the result drift, how it drifts, as we change configuration, how it drifts away at different positions here. So this is at the first position, at third, at fifth, and so on. So interestingly, when we are comparing unordered results, as the number of positions goes up, the overlap goes up also, right? And when you do ordered, you want to see that they are exactly the same order, and as overlap goes up, that goes down, which is kind of intuitively, it's correct, right? Then there was some others where we, invented a search quality criteria as overlap between title and query, and we found that in some cases we got a little bit of unexpected results. Things that were not doing better was doing better here, and so forth. Then we measured clicks by positions, and we got this, again, fairly intuitive charts, but these were interesting because you could compare different search results, along different directions. Another one was publication dates. So we had a freshness component where you wanted to show newer results first, and so that was, and there were some more uses. And so future work we have, so far we have computed click distributions per query. We are planning to do click distribution per user and click distribution per user per query. Once we have these figures, we could actually use some kind of collaborative filtering, or actually ALS kind of algorithm to impute preferred rankings for given a query and given a user, preferred rankings, and use it to re-rank the top page of results, right? So that's a learning to rank algorithm, but it's still kind of half-baked at this point, but this is what we have. And I think I'm done. Thank you for listening.
Thank you for the talk. There's plenty of time, it's a little bit early, so there's plenty of time to ask questions. Are there any questions about the talk, about Spark, maybe a little bit more about the Solr? Yes?
Hi. Very interesting talk. Thank you very much. I want to ask, you're considering all the queries, right?
Yes.
So you're taking into account only the position, but you're not taking into account the amount of characters that the user has to type, right?
The amount of characters?
The amount of characters that the user has to type in order to find the document that they want. I mean, you can improve the search engine by finding in higher position what you're looking for, but
yes.
you also improve it by finding earlier in your query, right? So if you type less characters and you find it.
Oh, I see. So what we did was we took existing queries, right? And basically we took 800,000 queries that we already had. And because we had the click ranks for these guys on the old machine, on the old system, right? And so this was our kind of our measure of user satisfaction. So if the user had clicked it, we assume it's relevant, right? We didn't actually change word lengths or anything. It's just, we took what they had.
And the second question, if you go to the graph that you show the distributions, is it weighted by the probability of this of every query, or it's?
This one?
Yeah. Is the these are the 80,000 queries, right?
Yes.
But they are not weighted to the probability of their to occur, right? So some queries are more probable and happen more often.
Oh, okay. No, we didn't actually consider that. We are averaging everything.
Okay.
Yeah.
Okay. Thanks.
Yeah.
Any other questions? Yep, sorry, I wasn't see there.
Thanks for your talk. It was very interesting. One thing I wanted to ask, you said you had about 800,000 queries recorded?
Yes.
So that doesn't seem like a huge amount. You could probably just iterate over it in one file. And I wanted to ask, what does Spark bring to the table that made it easier or better to do in Spark?
So if you think about this 800,000 queries, that's just the queries. Each query has 50 results. And we are considering, we are comparing, say, 4 or 5 search configurations at one time, right? So that kind of adds up. For instance, I was having trouble processing one. So before I moved to Spark, I was trying it locally on my laptop, and I wasn't successful. It's not like I wasn't successful. I gave up after a while. I think about 3 days into the job, I gave up and moved to Spark. Yeah.
I thought I saw one more. Yep, here in front.
I got sort of a small conceptual question.
Okay.
Would it be sort of fair to say, like, hey, we're looking for Solr if it can actually match the fast performance, but it would be really hard to test if it actually exceeds because we don't have that data. So you're basically saying we have fast,
well,
we just put Solr more or less on the same level and then exceed with later A/B testing.
Well, what happened in reality was we were waiting to hit the mark, right? If we, by any chance, we could have exceeded because it's an economic figure, right? We know how many users have clicked, and if on the Solr side more clicks happen, then it can exceed. But as it turned out that we just almost reached it and we switched. Yeah.
There's other queries where you don't have clicks.
Yes, yes.
And that's sort of still a gap.
There is definitely a bias, because one thing we turned out, like you mentioned, that because all the samples were taken from FAST, there are, if Solr shows something different, we have no idea how to, yeah, exactly, yeah.
I think that's most of the questions. So in this case, I would like to take this moment to have you all please applaud for our dear guest.